A claw hammer is used to pull a nail out of a board. The nail is at an angle of 60 degrees to the board, and an output force of Fo is applied to the nail pulling it out. The hammer head contacts the board at point A. Okay, and it's saying what is the mechanical advantage of this simple machine. So mechanical advantage is equal to the output force divided by the input force. And what will happen is you will have static equilibrium of the hammer. So you will say that this is the pivot, and if I draw F input and its force line, then this R perpendicular for the input is going to be the 0.25 meters. And if I draw this is your output force on your nail, and there's a force line here, this distance right here is, maybe we'll call that, it's 0.06 meters, right? And here's your angle 60. So I can draw, let's try to draw that triangle over here. There's a right angle between R perpendicular of the output force and this 0.06, and this angle right here is the 60 degrees. So this is opposite over hypotenuse. Its sine of 60 degrees is equal to the R perpendicular output divided by the 0.06 meters. So R perpendicular output is equal to 0.06 times sine of 60. So torque net is equal to 0, is equal to the input torque plus the output torque. Those should be equal and opposite. So what we'll have is positive, because this is counterclockwise force, Fi times R perpendicular input, and then the force on the hammer actually will be this way, right? It'll be Fo. It'll be a clockwise force, so Fo times R perp output. So anyway, you get the same magnitudes. So Fi R perpendicular I equals Fo R perpendicular O, and Fo over Fi, which is the mechanical advantage, is equal to R perpendicular input divided by R perpendicular output. R perpendicular input divided by 0.06 sine 60. It's 0.25 divided by 0.06 sine 60. 0.25 divided by, open bracket, 0.06 times 60, close bracket, equals 4.81. Three forces act on a rectangular object shown at points 1, 2, and 3. The directions and approximate magnitudes of the forces at points 2 and 3 are shown. Which of the directions below show the correct direction of the force applied on the object at point 1, which will cause the object to be in static equilibrium? Static equilibrium is that F net x equals 0, F net y equals 0, and the net torque equals 0. So we can define our xy axes, y up, x to the right. So right away, since F net x equals 0, F3 is in the plus x direction, so F1 must have an equal negative x component. It's got to be B or A. And then lastly, let's put the pivot at point 3. F2 provides a counterclockwise torque around point 3. So F1 must have a plus y component in order to give a clockwise torque. So that means it's B. Two children of mass 20 kilograms and 55 kilograms sit balanced on a seesaw with a pivot located at the center of the seesaw. So I think this, if we call that M2 is the larger child and M1 is the smaller child, it'd be farther away. If the children are separated by a distance of 3 meters, L equals 3.0 meters, at what distance from the pivot point is the larger child sitting in order to maintain the balance? So we'll call that x2. X1 from here to here, we also don't know, as it turns out. But in static equilibrium, you'll see that the net torque is equal to 0. So M1 will be pressing down in a counterclockwise direction, so plus M1 times G times X1 is the perpendicular lever arm there. And then M2 is pushing down in a clockwise direction, so minus M2 times G times X2. So we have that M1G times X1 equals M2G times X2. The G's cancel out in that equation, and we get X1, which we don't care about, is equal to M2 over M1 times X2. Now we need another equation here. I would say it is that if the children are separated by a distance of 3 meters, what that means is that X1 plus X2 equals this L of 3 meters. So that's our second equation. And now we're trying to solve for, I guess, X2 is equal to L minus X1. We have an equation for that, so we'll plug it into there. X2 is equal to L minus M2 over M1 times X2. Gather like terms on this side of the equation. X2 plus M2 over M1 times X2 equals L. Pull out a factor of X2. Maybe I'll multiply both sides by M1 just to make it look a little nicer. I've got X2 times M1 plus M2 equals L times M1. So X2 equals L times M1 divided by M1 plus M2. So it's 3 meters times the 20 kilograms divided by 20 plus 55. 3 times 20 divided by, I guess it's going to be 75 total, 0.8. The top of a uniform ladder of mass 11 kilograms, so we're going to put that ML equals 11 kg, rests, and length L, so I'm going to call L is the length of the ladder, 4.0 meters. Rests against a vertical wall, the bottom is on a horizontal floor making an angle, I'll call it theta, is 48 degrees relative to the floor. A woman, I'm going to call it MW, whose mass is 56 kilograms, is standing on the ladder 3.1 meters from the bottom as measured along the ladder. So I'm going to actually call this distance D, where D here is 3.1 meters. Friction on the wall is negligible, so I'll just say no friction. But the coefficient of static friction between the ladder and the floor is mu sub s, equals 0.410. Under these conditions, the ladder will slip. However, the woman has set up a box at the base of the ladder which applies an extra horizontal force F to the left on the bottom of the ladder. What is the magnitude of the force F needed to prevent the ladder from slipping? So we'll define the system to be the ladder and say that the ladder is in static equilibrium. So the extended free body diagram, kind of draw like this. Here's the theta. It's a uniform ladder, so M ladder G is down at some distance L over 2 from the base. And then there's another force, M woman G, down, and that's at a distance D from the base. Then there's the wall, which is going to produce a normal force. I'm going to call that NW since it's the normal force from the wall. And then you've got an upward force here, which I'll call NF from the floor. And then the other thing that you've got is there's actually two forces here. There's the force of static friction to the left, and there's a F to the left, both acting. So I've counted 1, 2, 3, 4, 5, 6 forces, and we will define plus y to be up, plus x to be to the left, and I'll put a pivot here at the base. Since there's, I guess, 3 forces there, 3 out of 6 are at the base, so we can eliminate those torques from the torque balance equation and put counterclockwise rotation is positive. So the 3 equations here are that F net in the x direction equals 0, F net in the y direction equals 0, and the torque net equals 0. So in the x direction, this is going to be the normal force from the wall minus Fs, because it's in the negative x direction, minus F equals 0. We're actually trying to solve for the force F, so flipping this around, you've got F is equal to the normal force from the wall minus the static friction force. And we also know that static friction is equal to Fs max for just about to slip. So Fs is equal to mu sub s times the normal force from the floor. We know that F net in the y direction is 0. We've got normal force from the floor acting up minus m mass of the woman minus the mass of the ladder. G equals 0. So the normal force from the floor is equal to the mass of the woman plus the mass of the ladder, total mass, times G. Because those are all the vertical forces. We can take this y balance force and figure out the static friction as being mu sub s times total mass. We can plug that in to here to get that the force we're looking for is the normal force of the wall minus mu sub s times the mass of the wall plus mass of the ladder, mass of the ladder, times G. Okay, so now we need to take the net torque equation. So this one's a little harder. We're going to need to get some perpendicular lever arms for the three forces. So what we've got, here's the pivot, here's that ladder. The three forces that are creating torques are going to be NW, and there's its force line, the woman's force, and that's that force line, and the ladder's force, M ladder G. Okay, so again, perpendicular lever arm, you drop a perpendicular between the force line and the pivot point in all these cases. So these ones are in that same direction there. I'm going to call this R perpendicular for the normal. I'm going to call this little one here R perpendicular for the ladder, and this bigger one R perpendicular for the woman. And there's your angle theta right here. And then by the Z rule, here's your same angle theta, 48 degrees up there. So what we can see is that here's your right angle. L is the length of the ladder. So for the normal force, the sine, I guess normal, is that sine of theta is opposite R perpendicular for the normal force divided by the hypotenuse is L. So R perpendicular for the normal force is equal to L sine theta. And then from these triangles down there, you have cos theta is equal to, this is maybe for the ladder, it's R perpendicular for the ladder is the adjacent divided by L over 2. If you can sort of see that triangle, this is L over 2, and then this distance is D, right? So R perpendicular for the ladder is L over 2 cos theta, and R perpendicular for the woman is D cos theta. So this torque equation becomes torque net is equal to the torque due to the normal force plus the torque due to the woman plus the torque due to the ladder. Okay, and this is equal to 0. The normal force is going to be, first of all, it's clockwise around the pivot, so it's negative NW, which is what we're trying to find here, times R perpendicular normal force, plus the mass of the woman times G, that's because it's counterclockwise, that's positive, times R perpendicular woman, plus mass of the ladder times G times R perpendicular of the ladder. You end up with NW times L sine theta is equal to MWG times R perpendicular of the woman, which is D cos theta, plus M ladder G L over 2 cos theta. So plugging in the numbers here, you've got the 9.8 times cosine of 48 degrees, pull out the G cos theta there, times 56 times 3.1 plus 11 kilograms times 4 over 2, and then divided by L sine theta, which is 4 times sine of 48 degrees. 9.8 times 48 cosine times open bracket 56 times 3.1 plus 11 times 4 divided by 2, close bracket, and then divided by open bracket 4 times 48 sine, close bracket, equals 431.5 newtons. And so your force that you're going to apply here is going to be that 431.5 minus 0.410 times the 56 plus the 11 times 9.8. So minus, open bracket, 0.41 times 56 plus 11 times 9.8, close bracket, equals 162. That's it. Here we're trying to tilt a refrigerator, which is this high, this deep, this wide, by pushing it horizontally a distance 1.3 meters above the floor. So I'm going to push against the front of it, I guess, here. This is 1.3 meters. This, so what I think is going to happen is I'm going to set this to be the rotation axis. The rotation axis would be the far side there, to just start tipping it, right? I'm going to push with this F, okay? And so meanwhile, there's going to be the mass of the refrigerator downward, pulling it clockwise. So I'm going to be pushing it counterclockwise, and it'll be pulling negative direction. So the sum of all the torques equals 0 is just when I am about to do that. So I think that is going to be, if we do the lever arm thing, the counterclockwise force is F times the 1.3. And then the clockwise is going to be mg times this width, I guess, or depth, possibly, divided by 2. I think it's actually the depth, if we're pushing on the front of the refrigerator. So then we just solve it out for F. So F is equal to m times g times d divided by 2 times the 1.3. So it's going to be the mass of 110 kilograms times 9.8 times this 1.0 depth divided by 2 times 1.3. 8 divided by 2 divided by 1.3. I got equals 414.6. I think that rounds down to about 410 newtons. Okay, the written problem says a man stands on a wooden board at point C as shown. The board is nailed to the floor at point A, so there's a downward force there, I think, from the nails. Then it's held up by a support, 0.75 meters to the right of point A. The center of mass is located at point B. The man's mass is 65 kilograms and the mass of the board is 45 kilograms. What is the downward force the nails must exert on the board to hold it in place? So this is a static equilibrium problem. We're just going to balance our torques. So let's draw an extended force diagram. We're going to define the system is equal to the board. And so we'll draw like this. There's going to be the force of the pivot, which is pushing up, F of I guess the support or something like that. Then there's going to be the force of the nails, which is what we're actually trying to find right there. Then there's going to be the force M of the board times G, and then there's going to be M of the man times G pressing down on the board there. So I think what I'm going to do is define the axis to be right there. I'm going to do, counterclockwise positive. And we're going to simply say that the sum of the torques is equal to 0 in order to be in equilibrium. So the sum of the torques is going to be equal to the torque from the nails plus the torque from the support plus the torque from the mass of the board times G plus the torque from the mass of the man times G. Some of these will be positive, some will be negative, some will be 0, but they'll all add up to 0. So since the axis is right where the support is, then the support equals 0. And then the nails, they're pulling, I think if they're pulling downwards, as I've drawn them here, that's a clockwise force. Counterclockwise. The clocks tick this way. So that's a plus this Fn times this distance, 0.75. And then we're going to, so this is equal to 0. And then these two are clockwise, so those will be minus forces. So minus mass of the board times G. That distance right there is going to be 1.5 minus 0.75. And then minus the mass of the man times G times this whole distance, so it's going to be 3 minus 0.75. So I guess I just have to solve that out for Fn, don't I? So I think it's going to be that Fn times 0.75 meters is equal to the mass of the board times G times, I think it'll be 0.75, and then plus the mass of the man times G, and it'll be 2.25. And so the normal force that we're trying, the nailing force, I guess, that we're trying to find here is going to be 9.8. We can pull out a factor of 9.8. Mass of the board is 45 kilograms times 0.75. Mass of the man is 65 kilograms times 2.25, and then all divided by 0.75 times, open parentheses, do it twice here, 45 times 0.75, close parentheses, plus, open parentheses, 65 times 2.25, close parentheses, divided by 0.75 equals, and I got 2352. 2350 to round it off there is the nail force, something like that. Newtons, don't forget newtons. Question 8. My shaving mirror is attached by 2 supports to the wall of my shower. So gravity pulls the mirror down, and there are 2 forces from the wall acting on the supports of the mirror. F1 acts at point 1, and F2 acts at point 2. So these are the forces acting on the mirror from the wall. Which is the following statements correct about the horizontal components of F1 and F2? Okay, so the trick here is what I have to do is first find F2 by setting the axis at 1. So if I draw this, here's 1. This is the axis of rotation. And here is mg, and here is 2. So what's going to happen is that mg exerts a clockwise torque around 1. So that means is that F2 exerts counterclockwise. So it's going to have to rotate it counterclockwise, so it's going to have a horizontal component is to the right. This is F2. F2 to the right. So that's that. And then next, find F1 by setting the axis at 2. So same thing, here's your axis, here's your mg, which pulls at the center of mass here, and here's your 1. mg exerts a clockwise force, clockwise torque. We need the torques to be 0, sum of the torques, so therefore F1 exerts counterclockwise. It has to twist it the other way, so this is going to have to be towards the left. F1 to the left. Which I think is why there's a suction cup on the mirror pulling it in that way, and this can just be a stick. You can kind of imagine that, right? It has to pull here, and it has to push here. And that's the only way you can have the sum of all the torques on the thing is equal to 0 about any axis, about the rotation axis at 1 or the rotation axis at 2.
So F1 has a horizontal component to the horizontal component to the left, correct? And F2 has a horizontal component to the right, so the answer is E. Okay, question 9. A uniform ladder leans against a frictionless wall as shown. Static friction between the floor and the ladder is sufficient so that it does not slip. Okay, it's static equilibrium. Angle between the floor and the ladder is 72 degrees. And the angle between the wall and the ladder is 18 degrees. The ladder has a mass of 7 kilograms, kg, and L is equal to 2.5 meters long. What is the magnitude of the normal force of the wall on the ladder? So you've got to find N. So the system here is the ladder. I think since I care about this normal force up here, there's also going to be a gravity acting down. There's going to be the friction force acting on it there. There's going to be another normal force, 2, acting there. I'm going to choose the rotation axis to be the foot of the ladder, where I don't care about a bunch of these forces, and then I'll just work out the torques of all the other forces. So, and let's draw an extended force diagram. So there's the ladder. The forces I really care about here are going to be N, and there's going to be mg. And here's my rotation axis. And I guess, again, there's Fs. And there's going to be normal, I don't know, call it normal 2. The normal force I don't care about. I'm going to say that the sum of all the torques is equal to 0, since it's not rotating. And I'm going to have to find, I think this is going to be the lever arm called dg of the gravity force. And then this distance from here to here is going to be dn, the lever arm of the normal force there. What I can do is I could draw some triangles and start with this one, I guess. If this, so by the Z rule, I think this is the 18 degrees. So let's say theta is 18 degrees. Then this is dg, and this is L over 2, half the ladder length. I'm going to use sine theta is dg, lever arm of the gravity, divided by L over 2. So dg is equal to L over 2 sine of 18 degrees. And then to find the normal force, the lever arm of the normal force, same triangle here, but now I've got L, the whole length of the ladder, and this is dn over here, and there's your theta. So now cosine theta is the adjacent divided by the length, the whole length of the ladder. So I've got the lever arm of the normal force is equal to L. So the sum of all the torques here, I'm going to say, is equal to, there's 0 plus 0. Those are the torques at the bottom because they're acting at the rotation axis, no torque. This is a counterclockwise torque from gravity. So it's plus mg times d sub g. And then the normal force is clockwise, so that's a negative torque of the normal force that I'm trying to find times d sub n. But I've already found these using the geometry, so I'll just plug d sub g into here. And I'll plug d sub n into here, these lever arms. And I've got, these are going to be equal to each other since the whole thing sums to 0. So I've got m times g times L over 2 times sine of theta equals normal force times L times cosine of theta. Either by luck or good planning, I can divide both sides by L. mg over 2 sine theta is equal to n times cos theta. So n here is just equal to mg sine theta divided by 2 times cos theta. So mg over 2 times tan theta, I guess. So it's 7 times 9.8 times tan of 18 degrees divided by 2. 7 times 9.8 times tan 18 degrees. And don't forget divided by 2, 11 newtons. So yeah, that's closest to answer A. Okay, last multiple choice question. A rigid uniform horizontal bar of mass m1 equals 1.5 kilograms is supported by 2 vertical strings. String A is attached to the top of the bar. 0.25 meters from the left end is connected to the fixed ceiling above. string B is attached to the bottom of the left end of the bar and is connected to the floor below. Okay, I get it. And a plant of mass MP is 3.2 kilograms is hanging from the right end of the bar. What is the tension in string A? Okay, so let's just say that the system here is equal to the bar. I can find the tension in the plant here. It's just going to be M plant times G, right? The tricky ones here are the tension in string B and the tension in string A. And I don't care about the tension in string B, so I think what I'm going to do is choose the rotation axis to be the left end of the bar, because that's where the tension is that I don't care about. But basically, yeah, I'm just doing that the sum of all the torques around that point is equal to 0. So there's going to be a counterclockwise torque from string A. So yeah, I've got this TB I don't care about. I've got this TA acting at some distance dA, I guess. And I've got this, which is M plant times G. That's the tension in this string, actually, in order to support that plant, is going to be at some distance, the whole dg, I'll call it again. But we know that length. So the sum of all the torques... Oh, wait a second, I forgot one thing here. What about the mass of the bar, M1 times... There's another torque there. I almost forgot about that. Just the weight of the bar, of the uniform bar, right? So the sum of all the torques is equal to 0. Is going to be 0 from that left end, and then it's going to be a positive plus TA times dA. And then it's going to be, these are both going to be clockwise torques, so they'll be negative. So minus M1 times G times D1, and then minus mass of the plant times G times dG. Okay, so, and I can rearrange that. The tension A times dA is equal to M1 G D1 plus MPG times dG. So the tension A is equal to M1 D1 plus mass of the plant times that length of the whole bar, all times G, all divided by dA. So I've got a 1.5 kilograms from M1 times 0.5 meters plus 3.2 kilograms from the plant times 1 meter, all times 9.8 divided by 0.25. Got 1.5 times 0.5 plus, well, just 3.2 times 1 times 9.8 divided by 0.25. I got 154.84 newtons. So that's going to be closest to 150 newtons. Great.
My name is Jason Harlow, and I hope you enjoyed this video. If you have time, please fill out the feedback form on my Google Forms available in the description to this video. There's also a link to the Google Classroom where there's a public discussion forum and a place where you can ask me a lot of questions. Also available as a link in the description to this video. I look forward to hearing from you. Take care.